So hello everyone. Today we'll be solving problem 3.35, a solid sphere of radius r that is centered at the origin, where the northern hemisphere carries a uniform charge density of rho naught and the southern hemisphere carries a uniform charge density of negative rho naught. And we'll be finding the approximate electric field with respect to r and theta for points far from the sphere, where r is much greater than our radius r. So this is how we would have it set up. We would have our sphere here with our axes labeled out. And then we would have our northern hemisphere labeled in the blue for rho naught, and then our southern hemisphere is labeled in the green for negative rho naught. So here we might be tempted to use Gauss's law because we hear the word sphere and we're thinking that there's spherical symmetry, but the problem is that it's not the actual spherical symmetry that we want. Since the sphere has two different uniform charge densities, that means the electric field is no longer uniform, and we can't use our Gauss's law here. So we're not out of luck here because we know we want to find the approximate electric field in respect to r and theta. We can use what we know as our multiple expansion. V of r is equal to 1 over 4 pi epsilon naught times the summation of 1 over r to the n plus 1 power multiplied by our volume integral. That includes r prime to the nth power, our Legendre polynomial of cosine of alpha, and our charge density. So starting with the first two terms, so for the first term we're going to plug in zeros because we start at n equals to 0, and this should be our monopole term, and then we're going to continue the summation. So our next number for n would be 1, and we write in all of our 1s. So we start to simplify because we know anything to the 0 power is equal to 1. Our Legendre polynomial for p sub 0 is equal to 1, and we're just left with our charge density in the volume integral. And for our dipole term, we see that we have 1 over r squared times the volume integral of r prime cosine of alpha times our charge density. So looking at our monopole term, we see we have 1 over 4 pi epsilon naught times 1 over r times our volume integral for our charge density. And we see that from the original problem, we need to take into account both the northern and the southern portion of this sphere because they have different charge densities. When we write this all out, we see that our charge densities, northern portion plus the southern portion, is actually going to equal to 0. So we actually see that our monopole term, this is me taking out the negative from that side, is going to equal to 0. So we have our monopole term equal to 0. Next, we're going to solve for the dipole term. I moved the whole multiple term down, and I'm just going to leave the monopole term here to the side so we don't forget that we already solved for it. And we're going to go ahead and start with the dipole term. So we have that our dipole term is equal to 1 over 4 pi epsilon naught multiplied by our dipole moment vector dotted with r hat over r squared. Our dipole moment is equal to the volume integral of our r prime vector multiplied by our charge density. So we need to know what our r prime vector is. We need to take into consideration our charge distribution and the azimuthal symmetry. We know that we have our sphere, and it's from our positive charge density to our negative charge density. All of these components that are pointing outwards to the sides will cancel out due to the azimuthal symmetry, leaving our r prime vector in the z direction. So we'll have r prime is equal to r prime cosine of theta in the z hat direction. Taking into consideration everything we just figured out, we can plug that all back into our dipole term. And we also need to remember that we will have our charge distribution for both the northern hemisphere and the southern hemisphere. I'm just going to make this wider for everybody. So we're going to have here, for our dipole moment, we are going to have our r prime integral is going from 0 to capital R, our phi is from 0 to 2 pi, and our theta is from 0 to pi over 2. And we're going to take the whole integral of r prime cosine of theta, rho naught, times r prime squared sine of theta, dr prime, d theta, d phi, plus our southern hemisphere. So our limits of integration for our r integral and our phi integral are going to be exactly the same, but now we need to pay attention to our theta integral, which will be from pi over 2 to pi, and we'll have our r prime times cosine of theta times negative rho naught times r prime squared times sine of theta, dr prime, d theta, d phi. So then when we solve for this, I highlighted the rho naughts because we're going to be able to take those both out. So we start off with rho naught. Our r prime integral turns out to be r prime to the 4th over 4 from 0 to r. Our phi integral is from 0 to 2 pi. And our theta integral turns out to be sine squared of theta over 2 from 0 to pi over 2. Then we have the same thing on our southern hemisphere. And again, the difference comes from our theta integral. And we'll have sine squared of theta over 2 from pi over 2 to pi. And so we know that we're going to get the same thing for both of our r and phi contribution, so we can go ahead and solve and take that out. So we have rho naught r to the 4th over 4 times 2 pi multiplied by sine squared of pi over 2 minus sine squared of 0 divided by 2 minus the southern hemisphere portion, which is sine squared of pi over 2 minus sine squared of pi over 2 over 2. So we're going to have sine squared of pi over 2 equal to 1. Sine squared of 0 is 0. Sine squared of pi is 0. Sine squared of pi over 2 is equal to 1. So now we're going to have 1/2 here and 1/2 here. Rho naught r to the 4th over 4 times 2 pi. We know that this portion is going to equal to 1, and we're left with rho naught times r to the 4th over 4 multiplied by 2 pi. So remembering this is just our dipole moment, we're going to plug this all back into our dipole term. So this portion is right here, and we're going to carry down our z hat from when we found r prime. Sorry about that. We have our dipole moment is equal to 1 over 4 pi epsilon naught multiplied by 1 over r squared multiplied by our r hat dotted with our dipole moment, and we have rho naught r to the 4th over pi over 2 in the z hat direction. So we know we're left with 1 over 4 pi epsilon naught times 1 over r squared over rho naught r to the 4th times pi times cosine of theta all over 2. Putting everything together, we multiply the 2 and the 4, which gives us the 8, and we can cancel out our pi's. So when we solve for the electric field, we know that to get the electric field, we can take our negative gradient of our potential for the dipole moment, and we just expand that here, taking our partial derivatives with respect to our potential in the respective r hat, theta hat, and phi hat direction. And we know that there's no phi contribution, so we can go ahead and say that this is equal to 0 based off of what we got for our potential. Now we'll solve for our partial derivative with respect to r and our partial derivative with respect to theta. So our negative partial derivative with respect to r is equal to negative partial derivative of rho naught r to the 4th cosine of theta 8 over epsilon naught r squared. So we'll take out the constants, and we're only taking the partial derivative with respect to r to the power of negative 2. We're left with our constants multiplied by negative 2 r to the negative 3rd, and then we're going to go ahead and do the same thing for our partial derivatives with respect to theta. Now taking our partial derivative with respect to theta, we plug in what we found for our potential, and then we take out our constants, and solving the partial derivative just with respect to cosine of theta, we're left with our constants multiplied by negative sine of theta. So both a negative times a negative, those signs go away, and we are left with a positive rho naught r to the 4th times sine theta all over 8 epsilon naught times r to the 3rd. And so if we put both of these contributions together, plugging them back into how we know to find the electric field, we're left with our electric field in respect to r and theta is equal to rho naught r to the 4th cosine of theta over 4 epsilon naught r to the 3rd in the r hat direction, plus rho naught r to the 4th sine of theta over 8 epsilon naught r to the 3rd in the theta hat direction. And again, taking out our constants, we can simplify a little bit more, and we get our electric field with respect to r and theta, rho naught r to the 4th over 8 times epsilon naught times r to the 3rd multiplied by 2 cosine of theta in the r hat direction plus sine of theta in the theta hat direction. And again, thanks for solving with me. See you guys soon.